Hi, in this video I want to show you how to measure density of a solid object with an irregular shape. So here is my test object and I want to find its density. So let's look at the experimental setup. Okay, so here is my experimental setup. I have a weight scale. This is a container filled with water. Here I have the object which I want to measure its density. I have a thread roll and I cut a piece of thread from that. Now first thing that I do, I weight my object. Okay, the object weighs 95 grams. Sometimes it's good to repeat the process to be sure that the measurement is correct. 95 grams, approximately. Now I connect the string to my object because later on I want to float this object into the water. So then I need to have something to hold the object. Okay, so I connected this thread to the object. Now what I do, I place this container on the scale and set the scale to 0. So the scale set to 0. Now I immerse this one into the water and measure and read the measurement. Now this one shows 13 grams. The object should not touch the sides or the bottom of the container. It should be floating in the middle of the water. Okay, so this 13 grams is the weight of water, is the weight of displaced water. So from that we can calculate the volume of this object, and we know the weight of it. Then we can calculate the density of the object. Okay, let's do this calculation. Okay, so the weight of the object is 95 grams and my weight scale has an accuracy of 1 gram. So totally we have 95 plus minus 1 gram. This is the uncertainty of the measurement. The weight of the displaced water is 13 gram, again plus minus 1 gram of uncertainty. Now we know that the density is mass divided by volume. So we have the mass of the displaced water, and the density of the water, we know it from experience. Usually we take it as 1 gram per cubic centimeter. But if you want to be more accurate, the density of water depends on pressure and also depends on temperature. Now the pressure dependency is very small. As you can see, from 1 bar to 25 bar, the difference is tiny. And on the Earth surface, we are close to 1 bar. So this graph is the one we have to look. The temperature, when the temperature varies, the density varies slightly. So for example, the temperature of my room was 22 degrees when I did the measurement. So it's basically 0.998 gram per cubic centimeter is the density of the water. Now in this measurement, maybe it's not necessary that 1 gram per cubic centimeter is already good. But if you do some very sensitive measurement, then dependency of the density to temperature is important and has to be considered. So now I can calculate the volume of the displaced water, which would be basically the mass divided by the density. So 13 plus minus 1 divided by 0.998, and then we have the volume of the displaced water. Now another source of error is the volume of the thread, because when I immerse the object into the water, a part of the thread will also immerse into the water, and that occupy a small amount of volume. Now for the swing thread that I used, every 20 centimeter I have calculated the volume is roughly around 0.01 cubic centimeter. So I have to subtract this value from this one, and basically the volume of the displaced water minus the volume of the thread will give me the volume of the object. Now I have the volume of the object, I have the mass of the object, I can calculate the density of my object. So the mass is basically 95 plus minus 1. The volume is 13.016. You remember that here it was 0.26, but then 0.01 is subtracted, so we have 0.16 plus minus 1.002. Now this fraction will be maximized when the numerator is maximum and denominator is minimum. In that case, we get the higher boundary of the density. And if you do other way around, so minimum on the numerator and maximum on the denominator, then we get the lower boundary of the density. Basically, if we do the calculation, we see that the density of this object is somewhere between 7.991 and 6.706. Now, if we do the average calculation, we see that the average density is 7.349. So still we see that the calculated density is within a large range. If you want to improve the accuracy of this measurement, we have to use a weight scale with better accuracy. Let's say instead of 1 gram, if we use a weight scale with 1 milligram accuracy. Then what we have is that these fraction, the higher and lower boundaries of these fraction will be much closer together. So the calculated density will be within a much smaller range, and hence we have a more accurate result. Now, if we use a weight scale with 1 milligram accuracy, we should notice that the volume of the thread will introduce more error than the error of the weight scale. So if it, instead of 1 gram, it will become 1000 of a cubic centimeter, but then the volume of the thread will introduce, for example, 100 of cubic centimeter in this case. So we have to be careful about the proper calculation of the volume of the thread and how much will be immersed on the water. Okay, so we have calculated the density of the object, and it turns out to be around 7.35 grams per cubic centimeter. What I can say is that that value is kind of correct, because this cup is made of more than 90% tin, and the density of tin is 7.31 grams per cubic centimeter. So our measurement and calculation was approximately correct. Now, one last thing that I want to mention is that the value of density calculated is the average density of the object. Now, if this object is made of uniform material, like this cup, then the calculated value is the density of that material. However, if the object is made of non-uniform material, like this sandwich, then the density calculated is the average density of the whole object. We cannot say anything about the density of the components, like this part of the glass or wood or whatever. Okay, so here's the end of the video. I hope that this information is useful for someone. See you maybe in another video. Bye.